Let's turn off this sunscreen. Let me do the marking the Lab1 here. Let's go question 1. Okay, recorder on. How do I know recorder is on? Check whether the file's there. File's not yet ready. Oh, this is a Lab 2 to 7. This is not the one. Let's start this one. Yeah, I think it's ready already. It's ready. Okay, that means nothing wrong with the recording session. See, it's appear here also. All right, let's get started. Okay, don't worry, we have plenty of time. Let's jump to the question 1. From this assignment to lab sheet, we got your lab sheet. Okay, I think you have to read it yourself, right? Make sure there's no plagiarism. Otherwise, you'll get a zero marks. Make sure the student is not asking for another soft copy from another student and then just submit it. Just changing the name and submit it. Sometimes we can detect all this with some of our tools here. All right, question 1. I think by now, you guys already installed the RP Spice. I presume that is done, so that we can jump straight into the question 1, which is the Ohm's law and Kirchhoff's law. All right. So what should we do? Okay, just copy this one. Copy these two. Copy these two. Under the question form here. So what I'm going to do is, usually I will start in a new page. I will just insert page break. Okay, I will jump straight now here. I leave a blank in the previous space, previous page. I start from here. All right. How come it start from question 3? I copy question 1. How come it become question 3? Puzzle. Remember, I just copy this one question 1. How come it appear question 3? How come they become 15 marks? Strange, huh? Is this some kind of a bug or something? Okay, here's how we start. I think the spelling is correct. Kirchhoff, right? This is a person name. Just never mind. We can do this later. Okay, so the first section should be the introduction, right? Remember, the first section is the introduction. Okay, so just go ahead and do it. Introduction. Remember also we need to use the correct font type. From here you can see times New Roman 12 point. Okay, apparently this is wrong. Okay, let's correct this problem. Here change to times New Roman. Change the size to 12. Okay, this is how we make sure that we are on the right track. Then since okay, now I in the next line break. Okay, I'm going to show one example how I do the introduction. Because the introductions size shouldn't be more than 1 A4 page. but it's going to be a bit longer for this, you know, for the first question, because this theory is quite important. Okay, so let's start with the Ohm's law. Let's start with the Ohm's law. Okay, Ohm's law. Then see, every time I copy here, then it become the different font size. Let's see. It's still the different font size, I think. Yeah, I don't know. It's never mind, never mind. Okay, let's try the other one. Let's try this. Yeah, this is better. I think now I should highlight all these thing, bold it. Okay. So I keep the Ohm's law here, and then following I'm going to discuss about the Ohm's law, because it's not a good idea to go straight away copy it, right? But I do not have time to rephrase the sentence, so I just going to copy it now. But I hope you guys have time. Whether you have time, you have to rephrase the things, this thing here. Complete circuit, the voltage across a register. The relationship between them is called Ohm's law. Okay. It's not nice to do that, you see. You cannot just copy word to word without rephrasing yourself. You have to make it your own sentence. You have to use your own words to describe it. But now we have no time for me to sit down and then look for a better sentence. So I'm going to just copy it. Okay. Insert. To make it stand out. To make it stand out, probably I'm going to put this one in the box like this. See, funny things happen again. The almost all disappear. It doesn't look nice, right? Let's centralize everything here. Strange. How to make it look better? Let me see. Because I'm not so good at the artistic here, so this is the best I can do actually. But if you can try to make it look better, see. I think there's something hidden here, you see. Let me bring this adjust a bit. Yeah. Now the O appear again. Okay, now I should continue. Actually, what we need to present to the reader is that the math form also. And for this one, I'm going to using a snipping tools. Okay, use a snipping tool like this. Oh, you see, this is what happened. Never mind. This is example, right? One. Okay. Equation one. Equation one shows the Ohm's law in mathematical form. Okay, that's for example. This one, we have Ohm's law, then we have to talk about the Kirchhoff's law, and for the Kirchhoff's law, we have two. Okay, I think just copy here straight away. Even though we have enough time then to do all this, right? But we still try to be a bit efficient. Okay, so this is the next one. Okay, I think I should highlight this one also. I should highlight the onslaught also, because they are the subtitle, the main title and subtitle. Actually, I would like to do this. Usually, my common practice is to make it a bigger font size here. There's a main title, subtitle, so that it make a difference here. Okay, so you have to go ahead and explain this too. Explain KCL and KVL, okay, in your fonts words, okay. Okay, I'm not going to copy and paste again here. I show you the first part only. Okay, I show you the first part. First, I want to see the definition of the Ohm's law. Then I want to see the mathematical representation, mathematical form. For the KCL, KVL, the form will look like this. You see, the mathematical form will look like this. This is a figure to help you understand this concept. This is the definition. So make sure you guys summarize all this information here and squeeze all this information into one to two A4 pages. You know, no more than that. No more than two A4 pages, because it's only how many marks? It's only 4 marks, I remember. Right? I remember the weightage is only 4. Oh, 2.5 only. Less than what I think. So it's only 2.5. So don't need to spend too much time here. So if you really run out of time, you know, probably you're in a rush, you are in the last day of preparing this one. Tomorrow's the due date. Probably you can quickly skip no, get this section done, because you know that it's only 2.5 marks here for this section. 2.5 out of how many? Out of 20, right? 2.5. I think it should be out 20. This is 15, 18, or more than 20. I think it's 30. I think it's 30. No, cannot say that. Cannot. Wait, should be 25? 25 times 4. 25 times 4, then we get 100, right? Should be 25. So should be 2.5 over 25 marks. The weightage is 2.5 over 25. If we times 4, then we get 100, right? 4 get 100. All right, let's come back to the next section. Now we slowly come to the procedures part. Okay, so like we need to get the format consistent, right? So I'm going to copy this introduction here. I'm going to use the correct font type and size. Copy here. Remember to leave a space, you know, leave a double line space here. So the next one is called the procedure. See, the font size is the following. Never mind. Let's change it back. Sometimes it's better to do it later. And for the procedure, I think you can copy the sentence. It's not okay, you know, because I don't think this is called a plagiarism, because you strictly follow the procedure, and then we need to follow exactly the same, the word to word, you know, we need to follow exactly the same procedure. We cannot use our own methods. So I'm going to copy the procedure here. Okay. So meanwhile, while we copy this line, it's a good time for us to just draw this circuit also, right? Draw this circuit on the LT spice. So I also need to copy this this figure. So let me use a snipping tools here and cut and paste. Every time we cut and paste, we need to be careful because we don't want to get into the plagiarism, you know. Okay, so we copy this one, then we type in the figure 1.3. You guys can follow, right? But I think the alignment here is a bit out. See, let me see. The default document setup is a bit, you know, unusual. Let me see whether I can change it or not. Where are the layout? Okay, let's change it to the margin. Change to a normal one. Where is the normal? Yeah, this is normal. This looks normal. But this one is slightly to the left. Let me bring it to the first line here. Let me do some formatting. Okay, formatting here. Oh, see, when we begin, it's better to start with a nice setup, file setup. Otherwise, you need to do this again. You see, this is all this time-consuming part. That's a bit better. Right. Now we are at the step 1. Construct the circuit below with the software LT Spice. Remember to save your file also from time to time. Remember to save your file. So I'm going to start LT Spice. Already open up here. So what we do is we start with a new schematic. Okay, so it looks like the exactly the gray color background. It doesn't look like the a worksheet at all. It looks like a blank document. Okay, now let's get started. First of all, the first thing come to mind must be the register, right? Okay, let's find the register. I'm sure you can find here, right? Can you see here on this menu bar? At the right hand side, top right hand side. Okay, this is one. Another place you can find is come to the edit. Under the edit menu, look for something called register. The short form is called R, capital R. Let me try this. I type Shift R. It won't appear, right? Let me try one more again. And again. Oh. Unless I put the cap lock, if I put the cap lock, then I press the R, then it will appear. Okay, let me see if I can delete this or not. Okay, let me try one more time. I put the cap lock on. My keyboard is a bit something wrong with my keyboard also. Let me try again. Okay. If I press Shift R, nothing happened. Shift R. If I keep my cap lock, they call the caps lock on, then I press R, then it will appear. Okay, but this is not what I use usually. I just present you the alternative way to do this. First is click here. Click here. Next is come here and select here, register R, and then the third way is the pressing the caps lock and then press R. Usually I will come to edit and choose a register. This is what I do, you know. Okay, I'm going to do the same. So how many do I need? 1, 2, 3, 4, 5. I need 5. So just go ahead and create 5. 1, 2, 3, 4, 5. Okay, we can also use a scroll bar to zoom in and zoom out. Scroll bar, the scroll on your mouse. And how to do the pen? The pen is really quite important. The pen, let me see how to do this. Oh yeah, you can use the what we call the left click. Left click, hold it, and you can drag it to the left and to the right. So this is very important. Make sure you're comfortable with all this shortcut here. Scroll, zoom in and out, click to do the pen. Okay. All right, that's to get you started. Now let's look at the schematic here. R1, R2, R3. Let's do exactly the same. We don't want to make ourselves confused. So we're going to align the R1 here, R2 here, R3, exactly the same. You see. So it looks like I need to. You see, when I select this thing here, it doesn't show anything is being selected. So this is a problem. Oh yeah, let me. You see, when I select all, this is not what I want actually. What is this? Run. Strange, huh? Because I pressed the cap lock or something. Wait a minute. I'm stuck somewhere now. It should be individual. It should not be all in a group. Where I make a mistake here? Let's undo something. But it's still together, you see. Never mind. Let's delete all the previous one. Because I remember I can move one by one. Okay, now it looks like they're all together like this. Let's start with R1. R1 should be placed horizontally. So I'm going to find the rotate view. Anything called rotate or not? Where is it? Let me look for it. You see, my window doesn't show all the icon. But usually the rotate is a Control R. Let me try Control R. Let me try. Wait a minute. Is it my software problem or it behave? Let me find the rotate the thing. Wait a minute. It should be some tool that allows us to rotate the parts, right? Usually we just right click or left click, no, it will rotate, or press Control R. I forgot what is the shortcut really to rotate the thing. Never mind. We have another. You see, now I come to this again. I zoom out all the way out. Oh yeah, I think here probably rotate something, right? Drag, delete, move. There's no rotate. Yeah, first need to highlight this one. Highlight. That's the menu here. Drag. The move is F7. Never mind, let me use a Google to search. Let me see. Control R. Press Control plus R or click the rotate button. Strange, huh? There's no rotate button here. Cannot be this one, right? cut. Probably I should change my screen size, I think, to see all the button. I think I should go ahead and change my screen size. I think my current screen size is not appropriate for the for this software. That's why I cannot see the rotate. But you say the control plus R should do it, because my keyboard has some funny things turned on. I don't know what this is. Looks like I'm sure you guys can do this. Let me see some message here. It's at the undo and redo button. Where is it? Undo and redo. Where is it? Cannot find it. Cannot find anyone. Oh yeah, rotate. My keyboard not allow me to use the control. I think the control is not functioning. Wait a minute. Let me see how can I solve my keyboard issue here. Because just now I remember before the class begin, I have some issue with my keyboard just now. Let me double check my keyboard again. Try to find it. Just now. But I'm not able to use a control anymore. You can see the I can cut. I remember last time I just press control, then it will rotate. You see, control plus R. Or probably I should keep my cap lock on. But still doesn't work. If I keep my cap lock on, my control just doesn't work anymore. It's not working anymore. Control R. Let me try one more time. You should use another control. No, it's not working. My control R is not working here. Neither the menu here. The menu here also show the I know gray color. Never mind. Let me start from the let me start from new one again. Okay. Before placing the component, that means I have to rotate before I placing the component. Probably this makes sense. See, I remember sometime that it's unlike other software where you can rotate. You know, let me do it again. Okay. Luckily, we have 10 hours to do this. See. All right. Let's start from here again. So now let's place the component. So before we let it go, let's press Ctrl R. Yeah, now I can rotate. See. That means we can only do this when before we place it down. If we finalize it, then we cannot rotate anymore. We just have to delete and redo again. Okay, looks like the student gave me a great help just now. What's the name? GCXY. Okay, thank you very much. You saved us some time already. All right, let's come back here. You see, guys, I need to do exactly the same layout as the figure 1.3. The next one will be L2, right? L2 should be vertically. So let's press L2. Okay, just nice vertically. So I find a nice location like this. And L3, rotate, Ctrl R. Okay, and then L4, let me see L4. R4 is here. It's not here, right? It's here. Make sure you follow exactly the same. Otherwise, later when I refer to R4, you are referring to a different R4. See? Now for R5, I need to rotate it horizontally. Just line it with R1. Okay, now I press escape. I press escape to undo it. Now I zoom in a bit. So what's the next step? Next step, of course, to join the wire. Looks like this is a wire, right? Wire. Oh, wait. Let's find the power supply here. The DC power supply with the, because I know the plus with the plus and minus terminal. Okay, let me show you where to find it. I hope your version that is the same. So first you come here, edit, and then you come to the components. Okay, everyone, come to the components, and then what in front of you is another window with all the name here. So you'll need to scroll it to all the way to the right hand side, all the way to the right, and look for something called the voltage. Yeah. Okay. Can you find it or not? Find the voltage. It looks exactly what we want, right? So it's okay. So we can have the DC, AC, whatever we want. You can see. We can do the setting later, DC or AC. But I think the default one is DC. Okay, so we place at this location. This come back again. Can I zoom in a bit? Pan. Let's see how to change this one. Oh, you here DC value, advanced. Here we can customize to a pulse or whatever. You know, exponential, sine wave, whatever, like AC also. Right now we just stick on the DC value. Okay, so the DC value, just put in this one, come back again and again. The DC value should be, there's no value here. Let me see if I can find or not. Where is the voltage? Hey, no. Should be at the this one. 5 volt. Okay, set to 5 volt. So this will be step 2. It will be step 2. Change to 5 volt. Okay, let's copy this sentence here. Step 2. Let's copy step 2 to our report. 2. Wait a minute. Let's follow the same font type here. Okay, now save the step 2 and come back to our worksheet again. Let's enter 5 volt and the resistance. I think we should key in a 0. Okay, 0 resistance. He didn't say the procedure here. It didn't say about the resistance value. But if we press 0, it will appear the 0 here. You know, it's a bit unusual. Let me do without the resistance value. Okay, let us do without the resistance value because the procedure didn't ask for resistance value. So don't key anything here. Because once you key in, you place the value here. And I think we also need to key 5 volt instead of 5. I think doesn't work. Let's put 5 volt. Make it look better. You see, make it look better. 5 volt. Whether we can move this 5 volt or not, let me see. To move this, you have to use the move F7. Use F7 to move it. Okay, press F7. To move. But what I want to move is to move the 5 volt here. Looks like I cannot do it. See, probably you learn how to move it. You let me know how to move this 5 volt. Never mind, this is just a cosmetic issue, you know, just apparent only. Not to worry too much. Now we need to fill in all the value for the each register here. So the next one, R1 is a 1K ohm. So what you need to do is right click, enter the new value for R1. So the default is R. So we just type 1K will do. Don't need to worry about the ohm symbol. Okay, do the same for all the resistor here, 1.2. Remember to put in the K also. Okay, I hope you guys can follow because I haven't encountered any issue yet. 2.4K, 1K, R4, and the last one would be 1.2K again. And if you ask me how about the name for the node A, B, C, D, E, I don't think you need to worry about this. Okay, this is just something we name the node and the branch, everything, and the voltage across R1 we call it a V1. So the positive is at the left hand side. Okay. All right, we have now we have how many students? 13 plus 9. We have 22 students now. Okay, we're almost reaching the second time tea break already. All right, let's get this thing at least. Let's wire this thing up. Oh, wait. Before we wire this, we need to place the ground here, remember? Always, there's always need to place the ground in the circuit. Otherwise, the simulation won't work. You know, simulation need to know where is the ground, where the ground is. So we have to come here, look for the ground. I think ground is really obvious, right? It's right at the second place here, second location. So just place the ground at the one. We need the 3. One here. Another one is here. One is here. Okay. Now it's all without the wire. It's really awkward, right? It's okay, you know. Now just join the wire. To join the wire, click on this yellow color one. You know, it's all really dark color. Only the one looks stand out the yellow color here is a wire. So just start from here. So I think where you start is doesn't matter. You can also make a turn 90-degree turn like this. How do you know it's completely connected? You can try to move this thing here. Let's say I try to move this R1 F7. I see. I can move the outside R1. The wire will not follow. I think this is a free software. We cannot expect too much. What is this? Wait a minute. You say I cannot save my file. Let me save again into this CT Lab1. Yeah, now I can. Right now, let's join all the rest of the wire. Here and here. I think something still look a bit strange, right? There's usually we can see there's something called a grid line or something like that. Actually, I think it should be here. I think from the previous experiment, probably I turn it off. I don't know whether you guys can. When you turn it on, it looks like this. It's better to help you do alignment. You see, with the grid on, but with the grid on, it's not easy to. When you print out, it's a bit ugly. You see. So when the time for you to print out and import it to your reports, I think you have to turn the grid off when the time comes. Okay, let's just continue to join all the wires. 90-degree turns, and then all the way to the ground. just make sure you follow exactly the same, don't try to be creative, design another new circuit. Then you'll be you're simulating a wrong circuit at the end. Yeah, you see, the one connected will show the box here like this. We show the dot like this or not like this. When you show the dot like this, it means it's connected. See, I'm quite curious about this here. There's no dot here. Probably, I hope it's connected, you see. If it's not connected, I think the software will let us know when we start simulation. Sometimes what we worry is that whether it's connected or not. We have to double confirm it. Right? So this one dot is confirmed. Is to confirm us it's connected. So let's join the rest. Okay, let's join the rest. Okay, guys, I'm done, and I hope I do the pen now. I'm going to move to the center. So before I continue, I need to save this one. Okay. All right, now. Everything looks nice, right? Everything looks okay. Whether you can follow or not, I'm quite worried. Looks like no problem, right? Otherwise, you already let me know. Okay, let's do the following step. Now we need to perform the so-called operating point analysis, OP, dot OP. Okay, now we come to second step. Click simulate. Okay, where is simulate here? Then click edit. Simulate edit. The last one here, I think. Yeah, the last one. Simulate edit. Okay, so it present you many options here. Looks like the one we want is the at the right at the end. DC operating point, short form OP PNT. DC operating point. So go ahead and select this one. So nothing for you to key in or configure it. See, unlike other options, you can key in something. For this one, is just select it, and then actually the syntax is here. Don't modify it, okay? This the command actually. They call it the command to activate the DC operating point. So you better don't modify it, okay? If you modify it, I think you'll mess up the simulation process. Okay, then click OK. So how do you know it's operating point? You can see the OP will be appear when you activate the operating point simulation. Make sure you can see this thing here, .op. Okay, now let's go to step number 3. Step number 3. Run the simulation, check the voltage and current, and you can also point at the node to check the voltage and the max current. Okay, just copy all. Follow exactly the same procedure. I think it's better to line up properly here. To line up properly. To make it look good. Okay, now guys, we are at step number 3. I'm going to run the simulation. You can see the paper running. Actually, this is the best way you can do it. Click on the run. Now what in front of you is the result for each node, for each current. Current is not at the node, as you know. Current is at the branch. But it won't appear here because this is not a very powerful software. It's not commercially purchased a software. It's a free one. That's why it's quite primitive. Everything is quite primitive. You need to refer back to the IR4, IR3. This one we know. IR3 is the current flow through the R3. here. Where is R3 here? Here. IR4 is the current flow to the R4. One thing to take note is there is no IR5. I don't know if one of you notice this or not. There's no IR5. But I think you should know, right, based on your basic understanding of the circuit. Because between this node and this node, we have the two ground. So what does it mean? 0 volt here and 0 volt at the other side. It's impossible for the current to flow, right? Both at the potential, the lowest potential 0, the ground voltage. So how can the current flow from 0 to 0? It's impossible, right? And from the theory side, it's impossible. But the software don't bother to show us also. I would assume the software to show us the VR5 equal to 0, 0 current, device current. But instead the software chosen not to show us anything. But as a student, we need to know that R5 will not have any current flow based on the finding that both ends are 0 volt. But the rest of the register, you should see the current flow to them. Now the next question is to ask whether this result is correct or not. Whether if we make any mistake in between, it will end up with a different result. But based on my observation right now, I think this result should be reliable, should be okay. So if you're getting the same result as what I'm getting now, I think you can rest assured is a correct result. Okay. So we are approaching the second break time. So we're going to do this. After that, we go for the break. Okay. So what we want to do is immediately import to our report. So what I'm going to do now is I'm going to press the print screen on your keyboard. On your keyboard, top right corner there, beside the scroll lock pulse, we have one called the print screen. I press the print screen, and then I come back here. I come to the default Microsoft accessory tools called the pens. I press Control V to paste my screen, and then I use the select. I select this screen here. I select this screen. Okay, and then I press Control C, and I think you know how to do this, right? Or Control X. I cut out this image, and then I come to my report. You know that you shouldn't press your result anywhere you like. You see, we have to be consistent. So the best place to place our result will be in the discussion, right? As you know, result and discussion. Wait a minute. I think should be in the result. Here, results. Okay, let's import it to our result section. But we are now still in the procedure. Don't worry, we can skip to the result right now. And is it here? We have to give it a name also. So what name should we give it to this table? Step 1.3, step 3, right? Step 3. Step 3. Figure, what's the figure number? Let's continue the next figure number. Let's find what is because the one is for question 1. This is obvious. The last one is the what? Let me find the last one. 1.3. So we should use a figure 1.4. Okay, because we cannot find 1.4 here. And then the next question starts from 2. So I think it's safe to use 1.4. Not to be confuse the reader if we double 1.4. So 1.4 is the step 3. result, simulation result, or step 3. Oh, step 3 better. Okay, centerize it. Now it look good, right? Okay, let's change this one to font, correct font size 14 and bold. Okay, leave a space. I leave a space here. I'm going to leave a space also for the following figure. Okay, now I come back to here again, step 3, under the procedure. And remember, we need to also to paste the evidence of our work, you see. We need to place evidence of our work to make sure you actually use a simulation or you just copy this image. So it's better for us to copy this figure here. So I zoom in a bit. I would turn the grid off, and then I use another tools called the Snipping Tools from Windows. I just go ahead and copy this. Okay, and I come back to my report again. Actually, I should place it in front of the result, you see. So it's okay. Let's change it again. Let's move in front of the result. Let's resize it to make it look better. I think this should be figure 1.4, you know. This is what I think. This should be figure. This should come first. So let's type 1.4 here. The simulation circuit. It's a step 1, right? Let me see. Is this step 1 or step 3? So it's step 1, right? Step 1. Let's capitalize it. Simulation circuit. And then here, this is changed to 1.5 now. Okay. We need to follow the sequence. 1.4, 1.5. Let's try to get centralize this thing a bit, centralize a bit. Because I think centralize will be better. Because if you see the lab procedure, I think the lab procedure just centralize everything, right? So this is centralized, you see. Yeah, this centralized here is a centralized figure. Okay, now we got the step 3 until step 3 done. So I show you step by step, all the way to step 3. Now it's time for us to go for a short break. Before we go, let's save our work. Before we go, save it. Let me double check anything wrong or not. Oh yeah. Just now somebody asked me about the name of our coordinator, right? I think it's I think I can find it here because now I recall somebody asked this question just now. The name of our course coordinator. Let's find here. Use one of this student. Miss Oy. Okay, Miss Oy. Miss Oy. Press it here. It's okay, you know. Don't bother by this. This all capitalized, right? I mean, it's okay. The important is the declaration form here. Okay, don't forget about this also. Your name and IC. Okay, now we save it. Then we go for a short break. At least we got the first one done. At least now you have some idea how to use the software. I think we are on the way to. Okay. All right, let's go for a short break. right, I'm back. I'm back. Stranger. Oh yeah, okay. All right, let's continue, guys. Where were we? Where is the assignment? Not this one. So your assignment 1. The assignment 2 is here. All right, let's go through one by one. So, number 4, record your simulation result in table 1. Okay. Because we need to fill up this table later on. Just copy this step and use it. Where is it? Here. Therefore, oh, this is not the right one. Okay, use the first option here. So it looks like we need to create one table here, table 1.1. Okay, this is what I'm going to do. I'm going to use the same old trick. I'm going to use the Snipping Tools to cut and paste this box into the pens, new pens. Okay, from here I'm going to key all my register value, right? I will key them all here in the box. Let me show you an example. How to fill in here. Let's use the text here. The voltage across resistor R1. Where is it? Let's come back to our circuit. Voltage across R1. So if you place, I think if you place your mouse here, 2.67, here is the 5 volt, right? 5 volt. So what do we mean a voltage across R1? That means the voltage across this component. That means you need to find the difference in the voltage between these two nodes. So the quick way is to find the highest one and multiply, subtract the lowest one. So 5 subtract 2.67, and without all the number behind it. Let's calculate. 5 divided, sorry, 5 subtract 2.67006. 5 decimal points would be good enough, right? It's very accurate, right? Yeah, 0.26. 2.32794. So let's key in here using the text. 2.37 2.3327, sorry, 3279. So it looks at 2.328 would be good enough. Okay, 3 decimal point should be good enough. I don't want to make your adding additional work to you. So I'm going to use the 2.328 only. Okay, forget about the V because all these are based on the unit volts. So we'll forget about the V here. Okay, so this is the first one. And I think you can continue to do the rest, right? I only show you the first example. So you fill out the next or the remaining one. Let me show you the current flow through the R1. I think the answer is from the simulation result. Current flow through R1 is this IR1. But this is given in the ampere, unit ampere. It's much less than 1, right? So we have to convert it to milliampere. So milliampere, you need to bring it forward 3 decimal point. 1, 2, 3. It's a 2.328. 2.328 milliampere. You see, here is also based on milliampere. So pay attention to this milliampere. So our results will be exactly same as the previous one, 2.328. Nothing wrong, you see, because it's 1K. Anything divided by 1K, voltage divided by 1K, you get the milliampere here. So it makes sense. See? Current is equal to voltage divided by resistance. So resistance is 1K, 1000. So this one divided by 1000, you get milliampere, right? So this makes sense also. And the calculated resistor value, if you divide this number by this number, you get 1K, right? So what I mean is, you take 2.327, 2.32, you get 2.328. It divided by the current 0.002328. You get 1K. So here is a 1K. 1. You get it? Okay, let me fill out the second row for you. Let me fill out the second row for you. Because the first one is so obvious, is 1K. Probably you are not convinced. Let me fill out the second row. 2.4. Let's come back to our circuit. 2.4 here. So we already have the node voltage for this node. We have the voltage for this node. Let's find the voltage for this node. Looks like the voltage for this node should be 0, right? Because this node is directly connected to the ground. Cannot be any voltage here, right? Because this is ground. You straight up, you see the node here, so the ground also. This node is same with this node. If you don't believe me, you right click on this node, it will show you 0 volt. So the difference between these two voltage potential is the voltage across the resistor R2, voltage across resistor R2. So it's obviously it's a 2.672. 2.672 kA. How about the current? Current can refer to the simulation result we got just now. But look for R2. R2 is a 0.00. So this one read as 1.1134. 1.1134, right? 1.113. 1.113. 3 decimal point will do. 1.113 milliampere, right? This the unit is a milliampere. How about the calculated resistor value? Should be based on these two, not based on the 2.4. You cannot just say the calculator is based on the 2.4. That means this is just the selected resistor value. This is not the selected resistor value. This is the calculated. So it must be coming from here. So we divide the voltage by the currents. But I want to point out here. I want to point out here is that where is my pen? Oh. I want to point out here later in the discussion section, right? Because this is still in the result section. Later in the discussion section, you can say use Ohm's law. V equal to IR. Therefore, okay, R is equal to V over I. Example, VR2 over IR2 equal to R2 equal to 2.672 volts over 1.113 milliampere. Equal to, okay. You can usually you can type it. You can type all the information like this in your report later on. in the discussion section to show that you understand how to do this. See, you are not just simply guessing or something like that. You actually know exactly what happening. So 2.672 divided by milliampere, right? So it's 0.00113. Enter. You get 2,364 because this is due to the round up decimal point issue. When we round the number up, usually we will not get something very close to the 2.4, but it's considered quite close, actually. I don't know whether it's more than 5% or not. Am I doing a wrong calculation? Because I'm using it based on 3 decimal point, 1.113. Oh, I'm missing another one here. Should be 3.1. Okay, let's do it again. No wonder I think something should be wrong. Cannot be so far away. Okay, let's do it again. 2.672 divided by 0.001113. 3.1. Exactly 2.4, you see. But we will say it's a 2400.72. We'll use exactly the number we get. 719, 3 decimal point. To be consistent with the previous one. 2400.719. And this is to ensure that our work is consistent. 3 decimal point and 3 decimal point. You see, we don't want to be because this is professional work, right? We need to be very consistent. Everything decimal point is the same. 3 decimal point, 3 decimal point, 3 decimal point. See, I mean we are very careful on this data taking. We are not simply ignore all these minor issue. Okay, I don't need to save this one, right? So of course you need to fill the rest. I'm not going to do it for you, okay? But I'm going to give you some time to fill out the form. So you just need to cut this form and import it into the result section. So I'm going to put it under the figure 1.5. And this is called table 1.1, right? Exactly table 1.1. But I think it's table 1.1 here is a bit awkward. It's in the center. Usually table is left specified. So I'm going to redo again. I'm going to cut only the box, not the table, not the text. I'm going to cut only the box. Forget about the original table one. So I'm going to key the table one here myself. Usually the table one should appear like this, the standard format for most of the technical report. Table one, usually they will not centralize it. They put on the left hand side. If you refer to most textbooks, you can see that they put the table one on the top, and they put the figure, the detail for the figure at the bottom. The table usually appear on the top. Okay, these for technical reports. You can see right here the table on the top right, and then the figures at the bottom. All right, so this is the what? This is step what? This is step 4. Okay, now let's continue to step 5. But I'm going to give you some time to fill the table. I'm not going to, force you to do it later on. So I'll give you some time for you to fill out the form here. I'm quite sure we have enough time to complete all, because the first experiment usually taking the longest time. We need to get comfortable with the software. Usually it will take much longer time. I think from the experiment 2 onwards, we'll speed up it, you see. But I have to allow you some time for you to prepare your data. Okay, please complete this form. This is what I can give you up to second row only. The 3 remaining rows you need to do it yourself. Make sure you don't copy from your friend, you know. Sometimes you look exactly the same, the graphic plot is exactly the same size. You know, you can tell that these two people are copying each other. Okay, just do that. So any mistake you make in the table, I have to deduct some marks, you see. That means you will not longer get 4.0. You no longer get 4.0 for the rubric. That's how I show about the rubric, right? The rubric. So if you make any mistake in between, anything in between, let's say under the result, probably you cannot get the maximum mark, the excellent. I will give you probably a good. So for the good, you get 3 times each, you get 24 marks here. You see, all the results are correct. See? If you make any mistake, you have to deduct some marks. But there's nothing between three to 4. Or it's either 3 or either 4. Okay? So either you get 3 good or you get 4 excellent. You will not get something in between. This is how we decide on your final marks. So I have a question here. I think the V1 is 5 volt. Let me double check. V1, what do you mean V1? V1 is 5 volt. Wait, we didn't say V1, right? We said the VR1. So if you look at the circuit again, of course this is a V1. Here's a 5 volt, of course, but here is a 2 point something, right? Because based on the simulation software, this node is V1. Okay, this node is V1. This node is let's call it node 1. Okay, node 1. So the difference is between the voltage across R1 is this voltage minus this voltage. So we get 2.3338. This is how the 2.38 come from. 2.38 is the voltage across R1. V1 is a power supply, you see. V1 is this power supply. But we are now calculating the voltage for this R1. It's not this one. It's not this one. It's a voltage between these two. We call the voltage drop. Another term is called the voltage drop. But for this lab, it's called the voltage across R1. So there are many terms you can use to refer to this voltage VR1. Some textbook would call it voltage across R1. I think the symbol should be appear like this, VR1. Another textbook probably would call it voltage drop. You know why the voltage drop? Of course, voltage will drop when we encounter any resistance, right? It will drop. So the voltage drop for me is more meaningful. Well, because it's starting from 5 volt at the right hand side. 5 volt at the right hand side here. After the resistance, it of course will drop, right? Some kind of resistance here. Of course, the potential voltage will drop. Will drop to 2.67. So in between, the voltage is 2.328 volt. So you have to understand this term, voltage drop, voltage across, and voltage V1. So the short question for the short answer for you is that V1 is not equal to VR1. V1 is V1, see? VR1 is a VR1. So I think this student probably confused, right? Okay. All right. So you understand is good. Okay, guys, I'm going to give you some time to fill up the table. It's okay for you to the first two rows, we are exactly the same. Everyone is exactly the same result. The next three rows, I think I'm confident that you can able to fill it up yourself. Okay, I'm going to give you some time. I'm not going to drag you into another. Wait. What I'm trying to say is I'm going to give you enough time so that you can catch up with us. Later when we come back, wait a minute, did I start the recorder or not? Let me see. Yeah, luckily, otherwise we need to I have to always remind myself about this, the recording. So I have another question here. Does the table already mention k ohm, so the answer should be 1 instead of 1. I think I type 1.00, right? I put the dot here, or your screen is too small probably. But I can see the dot here. Let me see my work file. Yeah, there's a dot also, but it's not so obvious, of course. It's a bit blur. Okay, so let me type the answer here. Okay, guys, feel free to ask question. Don't worry, okay? Don't worry. Because if you don't ask question, I don't know whether you can follow or not exactly, or if you have any doubts, you're going to carry the doubts throughout the semester. So it's better for me to clear out your doubts right now. How about the second one? 2, 4. Oh yeah, the second one, I think you're right. Oh, maybe this student is correct. This is wrong. This is wrong. Oh, I'm leading you to the wrong way actually. All right, guys. I think you're right. This student, your eyes are really sharp. You can capture this error. Oh, okay. Let me correct this part. This proof that I'm still human. No, I'm not a computer. The good news is I'm still a human. Humans do make mistakes. So 3 decimal point will do. 3 decimal point will do. Forget about the. Oh yeah, I think I should bring the 7 in. Since it's over 5 already, I should carry this forward. Become 2.401. So it's a bit better to show that this number is actually slightly different from the simulated value. The one we get should be after the round up, we get a slightly different value. It's okay, not to be exactly the same. When we're doing the practical one, compare the practical one with the ideal case. Of course, we will get some kind of error or something, right? When we come to the real world, we are not just exactly the same as the ideal case. So let me correct this part. Okay, I made a mistake. Okay, sorry about that. Luckily, we have a student to detect this error. Otherwise, I think until the end of the day, I still think that I make no mistake. You see, so this is a problem. Next time, I need to be very careful on this K. When I see the K value, I need to be think twice about it to make sure that I'm dealing with the K ohm. So I need to better be careful on this decimal point. I think this could be another good lesson for you. When you're doing any assignment dealing with the K ohm, you better double check your answer. Make sure your answer is based on K ohm, not based on the ohm. Okay, so this time need to remind ourselves again and again. So this question, this student asked a very important question here. Actually, this question is very important. You see, the Wi-Fi is not actually appear on the result. See, but I already explained to you, right? The Wi-Fi between this node and this node, they are zero. Zero for this node and zero for this node. That means there's no current can flow from 0 to 0, right? If you think the current analogy like the water analogy, water flow analogy, the water can actually flow from low to high, lower ground to higher ground, or even though you pour water on the floor, it can flow, right? But that's a different case because it still has some potential, you see. But when talking about the currents, from a zero volt to another 0 volt, it's impossible for the current to flow. So there's no potential to push the electron. There's no potential energy to push the electron across the resistor. That's why the quick answer would be it will be 0 volt actually. See, but there are many ways to explain this phenomenon. Okay, there are many ways to explain it. But usually I would explain it like the using the water flow analogy. I would say that if this node is a 0 volt and another node is also a 0 volt, how can you assume the current flow? But at least if you this is a 1K, if you using the Ohm's law to explain it, I equal to V over R. V is a 0 volt over the 1K. I think it's 0 ampere, right? 0 can be divided by 1K, right? But cannot be divided by 0, right? Can be divided by 1K. So based on the Ohm's law, is 0 ampere because there's no current flow for the, if there's no voltage drop, there's no voltage difference between these two nodes. Therefore, the current should be 0. So this number 5 here, need to be careful here. Need to be careful, okay? Need to be careful. I already give you the answer just now, but I don't want to make it too obvious. I'm trying to type the answer in. I'm going to give you some room for you to try out your answer. See, you have to believe yourself. You have to believe what you have learned. What is the voltage across the resistor? What is the current flow through? What is the calculated resistance? So I think it's quite impossible to calculate, right? It's impossible to calculate. So if something is impossible to do it, probably you can use something like the NIL. I don't know I think the short form for something like not relevant, something like that. You can use a not available. It means impossible to calculate. Probably another word is what? Not available. What is impossible? Then what's another term they use usually? I forgot. The word doesn't come to my mind right now. It's okay. Yes. Oh, right. Oh, I think we'll do one more 2 steps. You see, otherwise we'll be behind the schedule already. Let's. I believe just not get you enough time already. Okay, let's continue the next step number 5. Don't worry about the following question, right? Question 2 to 4 must be much easier than the question 1 because question 1 we have too many steps to worry about. Wait a minute, this one. Record. Okay, question 5 is here. Let's copy this. All right, now just like everything. I don't need to do alignment. Save it. Based on the simulated voltage and currents, calculate the value of resistance using Ohm's law. Yeah, of course, using Ohm's law. Now he's referring to the table 1.1 again. Compare the calculated result, calculated resistance value with their values in the simulator. Compare the calculated resistance with their value in the simulator. Okay. So we have to talk about this one in the discussion, right? So let's go to the discussion right now. Let's create another section called discussion. Okay. Let's put on the first point here. The first point. Based on the result and calculation for table 1.1. Is it 1.1 or table 1? I think 1.1, right? I think it's not table 1. See, I make another mistake. It's not table 1. I think it should be table 1.1. Yeah, table 1.1. So even though this is a minor mistake you make, you'll confuse the reader sometimes. Reader try to look for table 1.1, cannot find it. But instead it should be table 1.1. Yeah. So there's many places you can make a mistake. Based on the result and calculation from table 1.1, okay, answer this question. Their resistance value are tally. Are similar also. Just make it short, okay? Don't want to be breaking too much about this statement. Now we have the second discussion. You can, of course, you can go ahead and explain it furthermore. And you can explain about this 2.401 and 2.4 k ohm. They're almost the same, you see. 1 ohm doesn't make much difference when it comes to the k ohm range. 1 additional ohm doesn't make a big difference, you see. Less than 1%. So the error rate, if you want to talk about the error, the percentage error is less than 1%. Anyway, the less than 1% is considered good results. Because as a rule of thumb, usually we will not accept anything more than 5%. Anything more than 5% is considered not very accurate or not similar. You see, less than 1% is considered almost the best way. Not the best way, not the best. Almost acceptable. I mean, in the acceptable range. So this discussion number 1 is to answer this step number 1. Compare your resistance value and calculated value. So you said compare, it means you want us to compare in the discussion, you see, not under this step. Okay. So that the reader, when the reader read your report, scroll all the way down, then he comes to the discussion, he can see your result. Easy to read, you see, easy to read. So if you put this statement under the step, you'll confuse some readers sometimes. All right. Next. Number 6. Let me copy first, then I read. Oh, I didn't do alignment. All right, let's read it about it. This spelling error, right? This spelling error. Using a Kirchhoff's law and Ohm's law, determine the theoretical value for each voltage and branch. So tabulate the value in 1.2, 1.3. Compare the simulation result, show all the steps. Wow, a lot of things to do, a lot of steps. First, we need to determine the theoretical value. The next step is to compare. No, the next step is to tabulate in the table and then compare. At least 3 steps, see. So what do we do? Let's find 1.2. Let's find what table 1.2. Copy table 1.2. Oh yeah, just copy this to it straight away. I think I need to import it to the something like this, you see. But I only allowed to open once. Then I need to delete this one. So before I delete it, I save it. See, later I can use it as a reference. Save it first. After I delete, no longer can be recovered back. So see, let's have a new one. So new one, I will put. I will use as table 1.2. No, I'm not going to copy table 1.2. I just it's okay. I think let's go 1.2. 1.2 here. I think I have enough space here to squeeze in another 1.3. So hard to expand this table. Okay, let's try it. Let's copy 1.3. I need to fill out the form here before we can paste in, import it to our words. Yeah, just nice. We can squeeze both of them in here. So what do we mean the theoretical value for VS? Of course, the theoretical value for VS is just a 5 watt Z. Even though the simulated results, because the power supply cannot change, right? There's nothing to do the 5 watt. The theoretical value 5 watt should be remain as 5 watt also. So I would put in the 5 watt also here because it's of course you can discuss about it. But what I mean is the theoretical value from here you don't need to calculate. It's just you can just straight away copy from the circuit. Simulated, I think the simulated result also 5 watt, right? I'll be surprised if it shows a different than 5 watt. So it shows a 5 only. So I better follow exactly the same. I better follow exactly the same. So how about the V1 at not 2 here? Even though it didn't show where it's not 2. Let me see. I can force it to show the not value or not. Highlight the net. No, it's not the one. Label net. No. For me, we can force to show us where is the not 2. I think it should be here, right? Cannot be anywhere else. Oh, I forgot. Let me see again. Under the view, show anchor, spice, netlist. Never mind. How do we determine the 2.667 here? How do we determine it for the voltage for the node V2? Is for the V1. What is voltage for V1? Voltage for V1 voltage for V2. I think the voltage for V1. Let's refer back to the circuit again. Not this circuit, you know, this circuit, because this circuit tells us which is V1. So V1 actually is the voltage across the R1. On this table is referred to V1. So the theoretical value would be is something that you need to calculate it using the formula. This one is you obtain this value from the simulation result. So for simulation result, you can just straight away copy it from here. You can straight away copy from here. 2.672. Yeah, 2.672. But how do you calculate this one? 2.672. How do you calculate? Okay, you need some formula, right? You need the, but you haven't learned it yet, actually. You haven't learned it yet. You're going to learn it in the tutorial 2. So I cannot show you here. You'll be very confused to show you right now how to find this value. How to find this value here. Okay, let me see. Let me see here. 1 and 2. But you see, you have more time for you to prepare for this report after you attend the tutorial 2 and 3. I think by that time, after the class, probably you already know how to calculate the V1 here. The V1 from this node. Actually, you need to find the voltage for this node. Actually, the voltage for this node. Okay, but you need to simplify this circuit a bit. You need to convert this circuit so that you can find the node voltage here. You have to use some kind of a KCL and KVL. KCL and KVL to find this. Okay, let me show you some example. Let me show you example. Even though you haven't reached that step yet. Okay, so let me show some quick example here. Theoretical value. Okay, let me show that first. Okay. First, we use the KVL. KVL says sum of the voltage around a loop should be 0. See if you refer to the introduction, not here. If you refer to the introduction, let me show you. So if you not here, this is one. If you refer to the introduction, sum of all the voltages around a loop should be 0. Okay, so we go ahead and sum all the voltages around the loop. I mean, here, let's look at this loop. This is a ground. Here is already 0, so we can ignore this one totally. So we sum the loop along here. So we start from here. Here's a minus. We always start from the left hand side. So if you rotate this one, this will be the left hand side. This is the right hand side. So we start from 5 volt. We start from negative 5 volt. But you're going to learn about this in the next lesson, not now. Negative 5 volt plus V1 plus V2 will equal to 0. This is the theoretical formula. Okay, this is the first formula. So if you want to double check, I think we can verify this one immediately, right? We can come to our table there. Hey, where's our table? Let me find a table. I mean, these two voltage, if you sum up to get a 5 watt, right? VR1 and VR2, if you sum these two voltages up, you will get 5 watt. So what I mean is, you can further work this down like this. V1 is equal to, take the 5 watt across, become positive 5. This one across become negative V2, equal to 5 minus V2. V2 is a 2.672, right? I just try to verify, try to verify this equation whether it's correct or not. So this is a way I can verify it. So I should get this value right, 2.328. So this proves that this formula is correct. Okay. Is there any other formula? Of course, there's here another loop is from here. The 5 watt and then V1, then V3, and then V4 also need to be equal to 0. 0. See, there's the next equation. Minus 5 plus minus 5 plus V1 plus V3 plus V4 equal to 0. This is how I look at it. Minus 5 plus V1 plus V3 plus V4 equal to 0. This is so-called a KVL. But I'm not going to use the time now to go through all the theoretical part. You see, because you learn it in other session. I don't want to repeat again in other sessions. See. How about the KCL? KCL is the one that sum of all the currents should be equal to 0. Sum of all the current into a node should be equal to 0. So we talk about this, right? You see, let's look at this example. I don't think it will take us too much time. You see, I1 is going into the node. So pay attention to the word I use, the into. Current I1 go into the node, so it's a positive. Current I2 is leaving, so it's a negative. So they are totally opposite, right? I3, I4 into, I5 leaving. So if you sum all the current like this, you get 0 into one node only, into a node like this. Okay, so some will be we use the positive and negative to represent the direction of the current. This to make sense, right? Okay, let's come back to our circuit here. How do we make use of this KCL? Let's pick the B, because this doesn't make sense. This is only one node here, this the current and this current. Because the current flow would be something like this. Wait a minute. Let me use another way to show you. Let me use the other software called the Microsoft Edge. Microsoft Edge is such a friendly software sometimes. You allow me to draw on here on the screen immediately. You see, for this current is we're going start from here, right? Then you go around like this. This is the first loop. The second loop like this, right? This is a KCL. When we're dealing with the loop, it's the loop, right? Then we have to use a KVL. So KVL. When we use a node here, apparently it looks like a node to me. We should use a KCL. So the current here is going this way. The current here is going down. See, going down. This current, of course, going that way. So let's name this one I1. I1. Sorry. I said I1, but I wrote I3. What happened? Let's do it again. I1 going into the node. I3 leaving. Dealing with the node is a KCL. I2 leaving. So let's write it down. One in, two out. So these two must be negative, right? To make sense, they are going a different direction. This must be equal to 0. This is how we develop the equation with the KCL's law. KCL's law states that all the current into the node should be equal to 0. So from the equation like this, KVL and KCL, eventually you can calculate all this value, current and the voltages. So you need to fill out all this. Okay, you need to calculate and fill out all this table. But here you can just copy and paste, copy the simulated result and paste it. You don't need to calculate. This is called a simulated result. You need to compare side by side whether they are tally or not, their result are tally or not. So I'm going to copy this one because I use it at this stage. I don't think you can able to, calculate all this value. You need to attend the tutorial 2 and 3. So you need to attend the tutorial 2 and 3. After that, then you can calculate yourself, okay? So for now, I just going to paste this one in first. Later on, you can cut this out and then type in the value here again. I just need to show you what is to do for today. Okay, for today, you just need to capture the data. And for the theoretical value, you can do it later on, okay? Because you have time until November, remember? The due date is somewhere in November, 2 months from now. Should be 17 November, 17 November. How do they call it? They call it the table 1.2, 1.3. Change the font size. Oh, no. Yeah. 1.2 and 1.3. Better to leave a space between. Slightly a bit to the right. Save it. Okay, so I will not show you how to calculate this value right now because it's not the time yet. So we're going to leave it blank for now. Okay, because easily we expected to complete everything today, right? But this question is something you haven't learned yet, and also many questions following this. You haven't come to the theoretical part yet, so it's unreasonable for you to do it now today. So today, what we need to do is to do a simulation, and the theoretical value we have to wait until you understand the theory. It will be in the future, somewhere in the future. All right, so what do we do now? So we have to skip this part because we have to skip this step for now. I will not type anything here. Let's see, do we have step 7 or not? No more, good. So this is the last one. This is the last question where you need to calculate it. You need to determine also means to calculate, right? The theoretical value for the voltages and the branch current. Current, they usually call the branch current. Voltage, they call the node voltage. And they put them in the value here and in the 1.2 by 1.3 table. And then you need to compare. When it says compare, what it means is you need to discuss it in the discussion section. Show all steps during the calculation. So you need to show all your steps here, like what I did just now. Show all your steps like this. see how you calculate this value, how you calculate this value. You can just go ahead and type it in. You see, you can just go ahead and for example, in this discussion section, for the theoretical voltages, calculation are as follows. Okay, use KVL at Lab1, phi minus what is that? R1, right? R1, VR1. You can set your time by not worry about the subscript and the superscript. You know, just go ahead and type it in. Phi, actually, it's minus phi. You start with minus, right? Minus phi is no longer important. You see, because to save your time, plus VR2 go to 0. Then VR1 is equal to something like this. Okay, show every step. Okay, this is the first equation. Later we can substitute into another equation to find the unknown. Right now the R1 and R2 is still unknown to us, but we need more equation like this. We call the simultaneous equation, and then we have to use the mathematical tools to solve for these simultaneous equations and find all the unknowns. So here going to be all our unknowns here. We can use the equation like this, KCL and KVL. What is the formula I got just now? Forgot already. Oh, here, KVL, no, KVL is the, I wrote it down on here. I1 minus I2 minus I3 equal to 0. Just type like this, okay? Don't worry about subscript, because we don't have all the time we have. So if you really concerned about this, it's no harm to put a subscript. You see, I didn't say that you cannot do this. I just say that you can do this. It will not bother me actually. You see, what I want to see is whether you understand the equation or not, how to derive the equation like this. Whether it's subscript or superscript, it doesn't bother me sometimes. You see, this is just a assignment only. It's not a real report. You see, it's not a real technical report that you have to send to your customer. It's just one assignment that you have to complete it to fulfill the course. Okay, this is just my example only. Okay, I only do partially only because it's not the time yet for you to do all this. So you have to come back later on. You have to come back later on to complete this part. See, to find all the KCL, KVL, and then calculate all the unknown. Okay. All right, and type in. All right, guys, have to wait. Sometimes we have to wait. Okay. Is that all? Let me see anything we missed out or not. After the step 6, looks like this is the end. Then we come to something called the question. So I would just copy it into the result, right? Is it result or the conclusion? Let me see here. Let me double confirm. I always confused about this part. Oh, yeah, in the conclusion. Clearly answer the lab question. Answer the lab question. Just answer the lab question, okay? So here, discussion. Results. Discussion. The last one will be conclusion, right? All right, let's start the conclusion with the. I think it's better to start the conclusion first, then we follow by the question. Let's start. Okay, wait a minute. This is the top one. Okay, let's start the conclusion first, okay? And then at the end, we answer the question. So the experiment. So you have to write it yourself. I just want you some example only. Ohm's law, ACL, and AL are useful for circuit analysis. Okay, you need to continue to expand this conclusion. Okay, on the pen. That okay, continue to write. Okay, continue to write. You can look for any example how to write conclusion. Just how many marks for conclusion? 3. See, the most important still come from the result and discussion. So conclusion, you just write down your conclusion. Actually, as long as you write at least one paragraph, I will not bother you. So if you completely leave out the conclusion, leave out the question, then I have to give you the 1 mark here. No attempt was made to conclude. So as long as you put in at least one paragraph, 2 paragraphs, and answer the question. If you don't answer the question, of course you end up in this category. No question answering. See, conclusion is you have conclusion but no answer, no answers, no questions being answered. Okay, so you have to make sure that you have these 2 part question under the conclusion. For me, I think it makes sense to put the question at the end, at the very end, after your conclusion. So when I mark your paper, when I scroll all the way down, I see the result. I check everything correct, no problem. Then I see your discussion, how you find all the unknown using the formula, not using the simulation. So this is using the theoretical formula, theoretical equations to determine all the unknowns for the circuit. to find all the currents and all the voltages in the circuit. Without using the simulation tool, you have to understand this is called theoretical value. And then you come to the conclusion, and I see how you answer the question. Let me preview the answer. If we change the polarity of the voltage, suggest the value. So if the polarity, you know the polarity is a plus and minus, you change, right? If you change positive to negative, negative to positive, you change, then you answer. Then what happened? Actually, the answer is pretty straightforward. How can you determine the answer? Actually, you just can't need to come here. You just rotate this one upside down, and then you simulate. You see what you will get. You just probably you have to delete this part first. You delete this using the scissor. You delete it, and then you insert another power supply, and then you rotate upside down, positive facing downward, negative facing upward, and then you see all the result. Then you can answer the question 1 here. If the polarity of the voltage source change only one way, right? You can only change one way only. Rotate upside down. And what happened to the all other value here? What happened to all the other value? Okay, then for the part 2, determine the relationship between Vs, V1, V2, V3, V4. This one, you have to, based on your KCL and KVL, you see, this is called the relationship. This is called the relationship between R1 and R2. This is the relationship between these two currents, these three currents. This is what it means, the relationship. Okay, so the answer, the quick answer will be like this. But I'm going to give you the answer, right? This assignment. Based on KVL or KCL, I1 plus something equal to 0, something like this, okay? And then you try to, but wait. We only need to worry about the voltage, just not the current. So this is wrong. So we only need to worry about the voltages. Numbers will be R2. But this only concern the R1 and R2 voltages, but you need to also find the VR3, VR4, VR5. Okay, the relationship among all these voltages. See, I hope you. I'm quite sure you can do that. See, I'm quite sure you can do that. Okay, so far okay, guys. It's the time for us to go for another break. So you can say we arrive at the end of question 1. We have something we need to carry forward to the once we cover tutorial 2 and 3, then you can come back here again to based on the thing you have learned to derive the theoretical value. But for now, we have to leave it like this. Okay. This is so far we can get. We cannot get any further than this. You see, based on the thing you have learned so far, this is what we can get. But the importance of this lab is to get all the simulation result. The theoretical result, theoretical value, we can do it in the future. You not necessarily have to do it today. So now the time is 11. Actually, by 1 p.m. we have to complete the next question. I think should be able to do it. Because the first question always takes much longer time to explain all this requirement. Starting from next question onwards, we're going to do it a bit faster. And then you can see it going faster and faster when you're approaching the question 5. because you know how to do it already. All right, guys, now is the time for us to go for another break, another coffee break. Okay, I will come back later.